Summer, everyone is a bit heated. So, okay. Thanks again for everyone for coming to the Quantum Business Seminar in July. So we are very happy to have Himadri Shekhar to be our speaker today. So Himadri is an assistant professor in the Department of Physics in Indian Institute of Technology, Bombay since 2021. So before moving to Bombay, so he was a research assistant at the Imperial and also a lead minor fellow at TUBN. So Himadri's research focus has been to unravel the physical nature of correlations that connect the various parts of complex and explicit quantum systems, primarily from the perspective of theoretical quantum information and computing, optics, and many-body physics. So in recent years, he has been working on quantum dynamics and quantum information protocols in collective states, quantum light-matter interactions, hybrid system, aiming to develop and optimize quantum technology. And I think today he will tell us some stories about how to study the quantum properties of collective states that is a cavity. Okay, so here's your stage.
Thank you so much, Carol. Thank you for the nice long introduction. And yeah, and also thank you for the invite to Simon Fraser University and to all of you for attending the talk. Okay, so today what I'm going to be talking about is just some combination of theoretical approaches that we typically use to study quantum properties of collective states in a cavity. And I'll try to motivate why these kind of approaches are appropriate for certain kind of protocols that you want to study, right? And so let me begin with a story that I always start my talks with. Okay, I can't see. I need to press OK somewhere.
Yeah, just press OK. Yeah, good. And press the cross. And that's it.
Yeah, okay. So the story of light matter interaction or collective states in the cavity, the story begins basically from our understanding of how spontaneous emission first came into being, all the way to what we know as hybrid quantum systems today, right? So you can, sorry. Yeah. Is there a thing to turn this?
Yeah, I think this is the mic. You can just grab anyone.
No, to turn this on. I'll just use this as well. Yeah, sorry. So the first time we can think of light matter interaction in the sense that the light was quantized was probably in the study of spontaneous emission. Right? So if you have an atom that is excited and that spontaneously goes to the ground state, you want to know how does that actually happen. And for that, Weisskopf and Wigner first came up with a theory in which they introduced the notion of vacuum fluctuations. And that allowed you to calculate the line width of the frequency at which the atom would actually go to the ground state. And you could see a Lorentzian distribution around it, along with some lampshade. So that was the first instance in which you really needed light in some sense to be quantized. So you can do more than that. Purcell actually took it away further. He said your density of optical modes can actually lead to enhancement of spontaneous emission when you place this atom inside a resonant cavity. And this was the first instance in which you could engineer the quantized optical modes to have some quantum feature, which would show some kind of an enhancement in some quantum property. So in this case, he would show that you could enhance the spontaneous emission. But there were also studies in which spontaneous emission could actually be curved by engineering the cavity in a different way. And this was work by Kleppner and other people. But the next interesting part of the story was what is known as the Jaynes-Cummings model. So all this while we were just studying about spontaneous emission, you have an excited atom that just goes down and you lose this excitation. But Jaynes-Cummings first introduced the idea that this need not necessarily be the case. If you place an atom in and it really couples strongly with the cavity, information can actually flow back and forth, or excitations can flow back and forth between the atom and the light. So you don't necessarily have spontaneous emission. You can have this photon going back to the atom, and the excitation can actually oscillate in time, which gives rise to the famous Rabi oscillations. And in principle, gave the two dichotomous nature of one's the weak coupling regime where you have spontaneous emission and the strong coupling regime where you have this excitation being coherently exchanged. And all of this culminated in the famous experiments of Sergei Hirosh around 1996, for which he ultimately won the Nobel Prize in physics. And he was the first one who could show these Rabi oscillations by creating these Rydberg atoms in this extremely high quality mirrors and couple them strongly enough to experimentally exhibit Rabi oscillations. And in the process, he gave birth to the field of cavity QED in some sense. So most of light matter interaction that are relevant for quantum technologies that we know, in some sense or the other, goes back to the Jaynes-Cummings model and the experiments of Sergei Hirosh in some sense, right? So today, when we think about how these states are used in different experiments, you have experiments that still use real atoms in real cavities. You can think of the Misha-Lupin group in Harvard, where they trap rubidium atoms in photonic crystals. You have Russian-Water group. This is known as a whispering gallery mode of a cavity where you can trap a rubidium atom. But the story actually has now gone way beyond this. Now you can have artificial atoms which are created with like quantum dots, optomechanical resonators. You can have superconducting circuits, and all of these can interact with different kind of resonators or different kind of cavities to say. Okay, so these days when we talk about collective states, we talk of collective atoms, we talk about collective light matter interaction. These could be completely artificial objects that you've created, right? And beyond this, you also have like collective states that live in ensembles. You can have ensembles of spins, rare earth ensembles. You can have ensembles of real atoms like ultra-bold atoms, magnomic modes. You can have ensemble of qubits, as well as things like nitrogen vacancy centers. So in today's talk, we will focus on these collective states and how these collective states actually interact with the cavity in different regimes under different quantum protocols that you're trying to explore. So we'll look at two main protocols. In the first protocol, what we'll think of is how these collective states are used in hybrid quantum systems. In simplest language, a hybrid quantum system typically means where you have two or more interconnecting paths that coherently transfer information from one to the other to gain a synergistic advantage. For instance, you can say that you have a qubit, which is a superconducting circuit that is a bit lossy. So it's very good for processing, but not ideal for storing the memory. You can somehow couple it to something like an ensemble, like a nitrogen vacancy center ensemble or a diamond. And diamonds are not good at processing because you can't really control them well, but they are coherent enough to store the information for a longer period of time. So together they can create a hybrid setup in which your information both has advantages that are connected to processing as well as to being able to store it in a particular place in some sense, right? So in this sense, the diamond is the collective state that's existing in some interface. So the quantum bus here is the resonator that's running common to the two components. That's the third part of the thing. And so in the first part, we'll talk about what kind of theoretical approaches you can actually take to study these systems and how you can build upon this to see some interesting new physics that were perhaps otherwise not accessible. In the second part, we look at something that's a bit different from the first one. We look at how you can use collective atomic states. So these are nothing but BCs, which are trapped inside a ring like a toroid-like structure, and how you can use this for performing sensing. And here, what are we trying to sense? We are trying to sense the rotational properties of this BECs, okay, or study the rotational properties of these BECs. Okay, so let's begin with the first one. So for the first one, let's start with the very basic Jaynes-Cummings Hamiltonian. Okay, so sorry that I'm starting from something very simple. I'm sure all of you already know about this, but yeah, let me just touch upon this to build the story. Okay, so the simple Jaynes-Cummings Hamiltonian is, you can write it in a thing. So here I just have a single atom, which can be thought of as a two-level system, which is just talking to a single optical mode of a cavity. So what are the different terms? The first term is nothing but the energy of the atomic or the spin system. The second term is simply the total number of photon energies inside a cavity. It just counts the number of photons that are there inside. And the important term is the spin photon coupling. Here we have considered what is traditionally known as the rotating wave approximation, which conserves the total energy in the system. So what I mean by this is if there is a de-excitation in the atom, this means that a photon is created, or if a photon is annihilated, then an excitation is created in the atom. So the total energy in this interaction is actually conserved. And then you can have a driving term. So you can have a coherent drum, that's a coherent field that's actually driving this entire circuit, right? And together they form the very basic form of quantum light matter interaction that you can study. So, of course, there are a lot of other kind of interactions that can be present. You can have non-energy conserving terms, famously known as the non-rotating wave approximation or the counter-rotating terms that are typically used in Rabi models. You can have optomechanical interactions. You can have other kinds of nonlinear interactions that also exist in these systems, right? From our perspective, there's something very interesting. If you're just studying single atoms, then you can actually exactly solve the quantum dynamics of this, right? Because if you think about the effective Hilbert space, it's very, very small. So if you want to study how the atom is entangled with the photon field, you can take two atoms and study the entanglement between them. You can write down the entire dynamics exactly, and you can actually solve it. But this is no longer true if you're working with collective states, right? So because, as you can understand, if you have many two-level systems, the dimension of this system will rapidly increase. And typically in literature, if you look at how people study the dynamics of these systems, they use what is known as some semi-classical limit or some semi-classical approximation, right? And this is typically used in the study of quantum memories, in studies related to quantum sensing. And the argument here is if you have a large number of these emitters or two-level systems, you can factorize the correlations between light and matter and effectively write down a closed set of equations that you can then solve for the observables of the system. But you are factorizing all correlations between light and matter. So now if I ask you, like, can you study entanglement between the atoms in this system? Or can you study some non-classical correlation that would exist? You perhaps would not be able to do that. Okay, so how does this work? Let me look at the theoretical part a little more. So imagine now we extend the Jaynes-Cummings Hamiltonian to the Cavis-Cummings Hamiltonian, which is nothing but from a single spin or single atom, you're going to many atoms, right? And here again, you have the terms omega k prime, which is related to the different transition frequencies of each of the atoms. I'm not assuming that they are all identical. Again, you can have a single mode field. Again, each of these atoms can couple differently to the optical field. And similarly, you can have a driving. And now if you have losses in the system, you also need to take into account the various sources of losses that can be. So it could be a photon loss, it could be a dephasing of the spin, it could also be a de-excitation of the spins. So you in principle need to write down what is known as the Lindblad equation for the total system, right? So instead of solving for the pure quantum state and the unitary dynamics, you solve for the density matrix and you solve the Lindblad operator. So you can already see that this dimension is very, very high, right? So if you're working with pure states, like if you're working with unitary dynamics, this will scale as 2 to the power n. If you're working with density matrices, this will roughly scale with 4 to the power n, and equivalently for some dimension of the cavity. Okay, so if now I ask you, give you these numbers and say, okay, write down the density matrix and solve it for say 100 spins, or even not even 100 spins, say 20, 30 spins, it's impossible to do that. So how do people set up semi-classical equations for solving these large number of spins? The simple way is, yeah, you can write down the equation of motion for the various observables, A, sigma k minus, sigma k z. But you use the assumption that these kind of correlation functions can be completely factorized. So essentially, whenever I hit a term which says AC dagger, which is the photonic part and the spin part, I just decouple them and write them. So instead of having to solve a large number of set of such equations, I can solve just a small number of such equations and get my results for what the different observables would look like. But I'm throwing away a crucial part that I'm saying that there are no correlations in the system anymore. Okay. So, but if I still insist I want a quantum solution, so what are the ways you can go about it? So one way you can think of is, I can say I have an effective Hamiltonian that only exists in very, very low excitations. So I throw away most of my Hilbert space and I just limit my dynamics to the lower levels. Okay, that's one way you can assume. But yeah, there would be restrictions that you could only talk about very, very low excitations. You can use something known as quantum trajectories. Quantum trajectories are techniques by which, instead of solving the Lindblad equation, you actually solve a large set of quasi-Hermitian or quasi-unitary pure state dynamics and you average all over them. But that just gives you an advantage which scales quadratically with the number of atoms, but beyond a particular point, you can't use that anymore. So even this is limited to a very small spin ensemble. You can use techniques known as permutation symmetry. In permutation symmetry, you make the assumption that all the spins are identical, or if they are indeed identical, then you can use the permutational symmetry or the invariance of the permutational symmetry to reduce the effective dimension of the system. But even then, the dimension will scale as n cube, which will be extremely large if you are talking of a few hundred spins, right? So the method that we thought or we wanted to apply here is something that's called, that we called a variational renormalization method. And we called it this because it's similar to a family of tensor-network methods which fall under the broader umbrella of density matrix renormalization group. Okay, so using this method is slow, but it allows you to obtain exact quantum dynamics of the system for an appreciable number of spins in the system, in the hundreds, and also for larger excitations, which you could not have countered using some kind of an effective dynamics. Okay, so yeah, so are all of you aware of what tensor networks or these renormalization methods are? Okay, so then that works perfectly. Then I'll spend some time describing what it is and try to motivate why this is interesting. So at the heart of all tensor network methods or variational renormalization group, the fundamental understanding is, supposing you have a large Hilbert space, and in this large Hilbert space, now, yeah, so as soon as you have a large number of spins, this large Hilbert space is already daunting, then you don't know how to apply some kind of a numerical or analytical solution. But if you know from some fundamental principle of physics that your ground state or your specific, say, region in space that you're working with is weakly entangled, right? If this is weakly entangled, then it is ensured that the states will actually not occupy this entire Hilbert space. It will only occupy a much, much smaller renormalized or a truncated part of the Hilbert space. So how does this work? So a simple example is, think about a maximally entangled state. If you write down the Schmidt decomposition of a maximally entangled state, right? If you now look at what the reduced density matrices are, the eigenvalues of the reduced density matrices are full only if the state is actually maximally entangled, right? So you have half and half. Now think of many such spins. If your state is not maximally entangled, you will not have all eigenvalues in the reduced states. You'll have much lower number of eigenvalues. So you can actually transform to a state where you can throw away these zero or very, very close to zero eigenvalues and just work with the dominant eigenvalues. And this will always hold if your system is weakly entangled. Right? So this is the fundamental underlying principle for DMRG techniques, matrix product states, and tensor network methods. You write down tensors, you define some artificial dimension called the bond dimension, under the assumption that this dimension is sufficient to quantify the amount of entanglement you'll have at any particular partition of your system. Okay. So the question is, can you actually take it to open quantum systems? So because for us, we need to solve a open system. It's a noisy system. We need to solve for that. So we need to look at the larger superoperator space, not the regular Hilbert space, but we map everything to the larger superoperator space and we look for a similar trend there. And we can say that if your state is actually weakly correlated, it's not as well connected with what entanglement is. You can take the theory of matrices and write down something similar to a Schmidt decomposition, but it's not really clear what this Schmidt rank actually means, like how it's clear in the previous case that they directly mean imply entanglement. But you can assume that they are some kind of a correlation. And if your correlation is sufficiently weak enough, you can again renormalize and take it to a much, much smaller Hilbert space. So that's the idea. If you have a large number of spins, but you know that these spins will never correlate or entangle sufficiently well enough, you can map them to a smaller Hilbert space. And once you've mapped it there, you are at the liberty to apply whatever computational methods that you want. Fine. So let's see how does it look for us. We have a bunch of spins inside a cavity, and they actually look like a central body problem. So the spins actually don't talk to each other. They just talk to the cavity. So all effective interactions are mediated through the cavity. And in the language of old school DMRG, you can break it down into two parts, typical system and environment. Cavity is the central part of the central body problem. So the cavity dimension is never renormalized, but the spins themselves can be renormalized. What do I mean by renormalized? So the Hilbert space of the system is actually 4 to the power s, but I can always map it to a Hilbert space depending on the entanglement to a much smaller dimension, say d, which is the bond dimension. Similarly, for E, I can map it to, say, again, D. That's the maximum dimension I'll allow it to have. So effectively, the problem that lived in 4 to the power n reduces to 4 to the power d squared. And as long as d is something that's manageable for you, you can always do the calculations. Okay, so how would you go about doing it? In the larger super space, you can write down a similar relation, d rho dt equal to L dt, where L is the Lindbladian superoperator now, and rho is nothing but the vectorized form of your density matrix. Okay, and this L can then be split into individual components, where LIS is just the Lindbladian acting on the ith spin and the cavity. And if you can write it in this particular form, for very small time, say delta t, you can apply the Suzuki-Trotter decomposition. And what the Suzuki-Trotter decomposition allows you to do is, as long as delta t is very, very small, you can factorize all the exponentials in the sum in this product form, and the error that you get is only of the order of delta t cube. So if you take a very, very small time step, you can write it in this factorized form. And then the idea is, if you have a particular setup, you apply the first component to the first spin, say the kth spin, then you can move the entire system, renormalize the spaces, only isolate a single spin and the cavity, apply it there, and then you sweep through the entire spin and apply the, what you call the evolution to all the particular spins. Now, if you have swept through all the spins one after the other, what you would get is basically a single time step in which your density matrix has evolved from T to T plus delta T. Okay. So in this way, you can actually study the exact time dynamics of the quantum system. Right? So this is the way in which you can apply a variational renormalization method to work. So once you set this up, you want to look at a particular problem that is interesting, but you want to see like what special features that you can actually extract. So we applied this. So this was way back actually towards the end of 2018, 2019, and around 2021, we tried to apply to a set of different kind of problems. One of the first problems we adopted was to study how light interacts with what are known as atomic frequency combs. So atomic frequency combs are a bunch of collective spins which have discrete frequency distributions. So if these are, so you can consider that each of these spins may be a finite number of spins. There are sub-ensembles in an ensemble, and each of them have a discrete spin, right? So they can be created in a distribution by saying that somehow the distributions in between are actually detuned using some sharp laser or something like that. Okay. And one interesting feature, so this was shown by a lot of, I think, early experiments by the Nicola Giza group and Martin and Auxilius, I think, from the Nicola Giza group. You can use atomic frequency combs, and if you have light coming in, there are these very sharp periodic revivals that you get. And these kind of revivals can actually be used for as a memory operation. So if you can define the atomic frequency comb in such a way that the distance between two of these peaks is sufficiently large enough, so you can see that any information that is stored initially can actually revive very sharply after a fixed at particular amount of time, right? So this was one of the first instances where we applied our DMRG method, but instead of sending just any classical light, so these were solved using semi-classical equations. So the light by default has to be classical, it has to be coherent light. But in our case, we can actually send highly non-classical light, and you can see that the non-classical signature actually is not extinguished because you are using full quantum solutions to actually study the system. Okay, so in the second part, what we studied was, again, say supposing you have an atomic frequency comb. Now we want to send some initial cavity state. I don't worry about how this initial cavity state was created. I just assume theoretically that this exists. And if it interacts with the atomic frequency comb, I want to say that what does this state look like after some particular time t? So the idea is this optical state is stored inside the cavity, and then it comes out of the cavity after a particular period of time. And I've turned it and I've reduced the amplitude to imply that it will be distorted. But not only coherent light, you can actually send in, say, some random superposition, 0, 1, or 1 plus 2, or some other number, which are highly non-classical states. And then you can try to see how does it look after a particular amount of time. You can also send a cat state and then try to see, does the cat state actually survive? Or how can you engineer this entire system to study it? So one thing again, let me repeat. These kind of analysis you could not have done with the semi-classical equations, because semi-classical equations would wash out any such non-classicality in the photonic field immediately, right? So these were all done using the DMRG method, and we get some interesting results. So the first, you can see that we get the predicted collapse and revival, which are very sharp after a particular amount of time. You can see that the Wigner function actually, this is the Wigner function at some initial time t equal to 0. So the one on the left is just the photon number, not the state itself, but the Wigner function captures the entire state itself. So you can see that there is a parity transformation at the first revival time at t equal to 1. But at t equal to 2, the state actually returns back to its original state with very good fidelity. So if you're looking, if you're looking at the fidelity out here, you can see that the fidelity is high, but it's not sufficient. We need to actually try to see if there are ways in which this fidelity can be further improved. So the fidelity of this can actually be improved by adjusting the coupling strength in each of the tooth of the comb. So if you have an atomic frequency comb, which has different things, and each of the frequency combs couples differently with the cavity, if you play around with what the coupling strength is, you can see that the fidelity actually can be improved. So these are the fidelities for different distributions of this coupling. You can see there's an orange line in between for which you actually get the optimal fidelity in the revivals. Why does this happen? So, okay, sorry. So this figure also makes it clear, like I'm looking at how this coupling strength is actually distributed. Now I'm looking at different distributions here. So why does this happen? This happens because of something very strange taking place. There is an optimal distribution in which the energy gaps between the levels actually become identical. So we started with a system that is actually has a distribution of frequencies, which is an atomic frequency comb. But the perfect kind of synergy takes place when somehow you can manipulate the distribution in such a way that the energy gaps are more or less identical. So in that sense, they interfere perfectly, and they tend to give you back a higher fidelity at each time revivals. So if you analyze what are the energy gaps, the point at which you actually see the least gap between the different energy levels of the ensembles, that's where actually your fidelity is maximum. So this analysis, you can just do it analytically, and you'll see that the numerical results for DMRG will actually support these kind of outcome. Okay, so this was one of the key results that we had, and which shows that the technique can really be used to get some interesting results. Recently, we tried to, so this was in the group of Johannes Fink and Institute of Austria, Institute of Science and Technology, Austria, IST. And there we tried to mimic this using superconducting qubits. So you can have like an ensemble of superconducting qubits. So it's not really an ensemble, they're just 5 superconducting qubits inside. But even if you just take 5 and you don't arrange them in a particular manner, you just get the usual Rabi oscillations. But if you can actually arrange them in the manner of an atomic frequency comb, you can see that there are these specific revivals that you can get. So this is what the picture of the architecture looks like. So these are the 5 active superconducting circuits. Yeah, I don't think I'm qualified enough to explain this to you very carefully, but I've just flashed some numbers. So the omega z's are of the order of 5 gigahertz with spacing of 30 to 50 megahertz. And the coupling is of the order of 30 megahertz. And you'll see that, yeah, the coupling is higher than the losses in the system. So it says that it's operating in the strong coupling regime, right? And you can see, if you just look at the results, you'll see that there are specific revival times that depends on what the comb spacing is, or the spacing between the different tooth in the atomic frequency comb is. You get different transmission spectra, which shows that each of the peaks are actually giving rise to polarity tones. And then you get this nice revival. So you can actually demonstrate the entire thing using superconducting circuits. Right, so this is one additional slide. It's not that important, but this just highlights that using an ensemble actually makes your system much more robust compared to just trying to study this using a single spin or single atom if you're trying to study Rabi oscillations. So these are, so rest states of ensembles are saturated at much, much higher energies compared to what a single superconducting qubit would face. Okay, so Kero, how much time do I have? Still have 20 minutes. Okay. Okay, so this was the first part of the talk. So, and the theoretical method I wanted to use is how you can use DMRG-like methods, especially when we want to study light matter interaction in a way where we want to really look at the non-classicality of what the constituents, non-classicality of the constituents that are participating in the dynamics, right? So my next, the topic that I'm going to talk about is slightly more recent. which was done by one of my PhD students. And this is about how you can use collective atomic states for some kind of a quantum sensing. So in this work, we looked at something very simple, but I think the way the theory developed, I think it was quite interesting. So let me first describe what this setup is. So what you have is, say, a Bose-Einstein condensate in a ring, right? So it's like a toroid and you have a Bose-Einstein. So it has a specific angular moment as it is going around this particular ring, right? Now what I do is I take orbital angular moment of light and I shine it on this. So this orbital angular moment of light has some L, which is the intrinsic OM of the light. And I take a summation of L plus L and minus L and I inject it. And this creates a particular optical lattice inside this, what we call inside the toroid, because of the shape of the OM. So these are the points at which the atoms will start interacting with this light, because that's where the intensities are. But the light that I'm shining in has a very, very low power. So it does not actually disturb the core condensate. It just scatters a few atoms at these points. And these atoms would scatter with, say, L plus L, L plus 2L, or L minus L, L minus 2L, depending on, so what the sites are. Right? So my idea here is I have the entire condensate. I want to detect it in a non-invasive manner. So I shine this orbital angular moment of light with very, very low power. I scatter some of the atoms, and then I look at what the output light is. And by looking at my output light and looking at the spectrum of the output light, I try to then come back and calculate what the angular momentum of the system actually was. Right? So again, I have a BC with a particular angular momentum. I don't know what it is. I have light with a specific angular momentum L. I shine it in such a way that very small scattering processes take place, few atoms scatter. And on the other side, when I'm looking at the output light, this fine small scattering should be good enough to give me some signal that can allow me to sense what the angular momentum of the actual BEC is, right? And for me, like I don't really work with BECs much, especially atomic BECs, but you'll see that if you look at the equations and you reduce it to some effective model, what you get back is your standard cavity optomechanics. And once you get that, that is a place where I'm more comfortable working with collective states and cavity optomechanics. And then I can bring on my toolbox and try to tinker around and do different things, right? So this is what the Ross-Pittsburgh equation of the entire condensate would look like, along with the cavity field and the driving. Yeah, so you can see that there is a quadratic term G there. That is the famous nonlinear interaction that you get in the Ross-Pittsburgh equation. And the assumption that I make is the wave function or the BC operator can basically be written down in terms of three operators. CP, which is the original condensate with some angular moment LP. And then I have a C plus, where I have very, very few photons, very, very few atoms, which now have angular momentum LP plus 12, and very, very few atoms which now have LP minus 12. And how do I impose this? I say that CP is so large that I can replace it with a C number. CP, the CP divided by CP is still N. And I can replace CP with just a C number everywhere. And then I can redefine two operators C and D corresponding to the two scattered modes. One that's scattered with plus 12 and the other that's scattered with minus 12. Right? That's all that I'm doing. And now if I rewrite this equation, you can see that I get back something that looks very similar to our usual James-Cummings that we were talking about. But here we have three bosonic modes, A, C, and D, where C and D look very similar to mechanical modes or sideband. Yeah, these are just the sideband modes of that we see look like mechanical modes. And you can see the interaction here, A dagger A with XC and XD look very similar to your usual optomechanical interactions. right? And XA and XD are just the quadratures of the modes C and D. Okay, so the question is, why is this helpful? How does this give us anything? So again, I write down the Hamiltonian. I can write down the Langevin equations for these kind of the entire for the quadratures of the C and D and the photonic mode. And then I have the noise terms EC, ED, and AN at the back. So I can use input-output formalism to introduce noise into these systems. And I have omega C, which gives you this expression. So one point I need to mention is the capital G out there is the optomechanical interaction between the scattered atoms and the optical light. Small g out here with this curly Z, this is the interatomic collision term, right? And we can actually ignore this for the analysis, because if you do the entire analysis, you'll see that this collision term just gives you a shift in the frequency detection and does not qualitatively change the physics. And you can see that if I ignore G out here, omega C becomes nothing but your small omega, right? And the quadrature components you can see would now oscillate with this capital omega C and capital omega D frequencies. So if I were to somehow find what omega C and omega D is, I can actually find out what LP, or the angular momentum of the condensate, is. So in this thing, small l, I is the moment of inertia, or small l and I is something I already know because those are my experimental parameters. But knowing these two frequencies, I can actually find out what LP is. And how do I do that? I can study what the spectral output of the optical field is using homodyne detection, right? Experimentally, if I do a homodyne detection of what the spectral output field is, X and C both oscillate with omega C, and they are directly related to the output field. So if I look at what the spectral output would be, they would give me peaks at omega C and omega D. And the difference between the two peaks will directly allow me to estimate what the angular momentum of the system is, of the atomic BECs. So numerically, how would we go about solving it? So how do we solve these equations? We again use input-output formalism. That just input-output formalism allows you to use the Langevin equations and play around with the noise as you deem fit. You can find monostable solutions to this, and you can linearize the equations of motion around these monostable solutions. Then you can Fourier transform them to the frequency domain, and then try to find out what the analytical expression of the spectra looks like. So once you have that, then you just find out where your spectra is actually peaking, and around that quantity, around those frequencies, you can find out what is the sensitivity of your measurement or what kind of noise you have in the system. Okay, so there are two key features that will come up. So if these are the spectra that you're measuring, there are two things. One is there is a lot of noise in the system. So you need to study how you're managing the noise in any sensing protocol. And the second is, what is the sensitivity of the measurement, right? And these are the two quantities that I want to improve. I want to reduce the noise, and I want to make the measurement more sensitive. So there are basically three kinds of noise in the system. One is the short noise. Since the light itself is very, very weak, and the number of atoms that are being scattered are also very, very few, what you're detecting is essentially just some particles hitting some board. So there will be a lot of short noise in that. The second is radiation pressure or back action noise. It says that if you have different quadrature components, making any measurement on one quadrature tends to affect the other quadrature. And that can introduce a noise in your system. So you need to somehow measure it in such a way that there is no back action due to the measurement process itself. And of course, we have the usual thermal and quantum fluctuations. So there are two ways in which we try to attack these. First is the standard using squeezed noise. So in the input-output formalism, you use vacuum fluctuations that are squeezed. You'll see that squeezing is actually very, very effective in getting off short noise. And this is already known. So in low powers, short noise is effectively mitigated by using squeezing, you can see that this allows you to achieve higher sensitivity. But what we observe is using squeezing alone is not sufficient for you to take care of radiation pressure or back action noise. For that, so you can't break the standard quantum limit. You can't lower the noise to break the standard quantum limit. For that, you need to use some back action evasion techniques. Okay. So how do we do that? So for the squeezing in the input-output formalism, you just need to ensure that, so in input-output formalism, how you introduce squeezing is you just say that you have the usual coherent field, but then you have a different port that can introduce squeezed vacuum fluctuations in the system. So you write down the same set of equations, but now the noise that you're adding at the end, that is squeezed. Okay? And then you can immediately see that, so this is the sensitivity of the measurements that I'm doing. So sensitivity 0, 0 divided by sensitivity with finite squeezing angle and squeezing amplitude. So larger this number, the better is your sensitivity, because you want the sensitivity to actually go down, right? So you can see that slightly introducing even some small amount of R, like somewhere in the region of 1, and some squeezing angle. There's certain specific squeezing angles corresponding to your homotype detection angle and other things where you can actually improve your amplitude. Improve your sensitivity. But if you look at the noise, so that plot there shows what the noise looks like without any squeezing. So the green line out there is the quantum limit that you can hit at a finite temperature T. So that corresponds to this green line out here. And the dark green line is actually the quantum limit you would hit if you just set the temperature to 0. So you can see the squeezing will actually allow you to break the quantum limit at that particular temperature. But it will not allow you to break the ultimate standard quantum limit. So, and this all happens at low powers where squeezing is actually effective. So it can actually break the quantum limit at some finite temperature T, but not the standard quantum limit. Right? So that's because the squeezing has taken care of the short noise, but not of the radiation pressure noise. So now you have to come up with a mechanism that can actually even tackle the radiation pressure noise. Okay. So to go beyond the standard quantum limit, we use a technique known as back action evasion. So in back action evasion, what you want to do is, as the word mentions, you want to avoid the back action noise. How you achieve this is, in generic terms, it's called quantum non-demolition measurements. So can you measure a quadrature in such a way that the back action of this quadrature on the conjugate does not actually exist? Or even if it exists, it is minimal. So supposing in this scheme, we use two different drives, which are at, see, if omega A is the driving frequency of the cavity or of the input light, you introduce a bichromatic drive, which is omega A minus omega M and omega A plus omega M, where omega M is nothing but the average of the frequencies of the two optomechanical modes or the sideband modes of the BEC. Right? Now, if you linearize it around the steady state, you can write down an effective Hamiltonian, and you can see both this Hamiltonians, both the C and the D modes now oscillate with the frequency omega M plus capital omega and omega M minus capital omega here. Okay. And if you can estimate what omega is, omega by definition will give you omega C minus D by 2. And you can see estimating omega again can allow you to estimate what the angular momentum of the BEC is. So again, like in the previous case, we were looking at two peaks, and we were looking at the difference of the two peaks to estimate what the angular momentum is. in this case, instead of looking at the two peaks, you just need to focus on one of the peaks, which is omega, and that will allow you to calculate what the angular momentum is. Now, how does this actually achieve back action evasion? So let me simplify this and write it under the rotating wave approximation. Right? So in rotating wave approximation, I've thrown away the counter rotating terms. I just keep the energy conserving terms. And if I write it under the rotating wave approximation, just look at the equations of motion for P and Q. So P and Q are for the optical modes, and X plus and minus, P plus and minus are for the what you call the sideband modes or the scattered modes. If you are measuring, say, the P quadrature, the P quadrature only depends on the X plus quadrature out here. And the X plus quadrature out here actually depends only on the P minus quadrature. Right? So you have the X plus quadrature and the P minus quadrature, they depend on each other. And every time I want to make a measurement on P, every time I want to make a measurement on P, I just need to know what X plus is, and X plus is depending on P minus. But their conjugate variables are actually P plus and X minus in the way I've written it. So even though I'm measuring P and I'm affecting one of the quadratures, its conjugate variable is actually decoupled from it. Yeah, so typically what do I do? I want to measure the P component and it's going to affect the conjugate component. But here the conjugate component is actually completely decoupled from the equation of motion. So it doesn't matter if the conjugate component keeps getting worse and worse because it does not depend on what you're trying to measure. So there is no effect of the back action. So even if there is back action, that does not affect your measurement outcome. Right? So, but yeah, outside the non-rotating wave approximation, you'll not get such a perfect decoupling, but you'll still get a lot of gain in simply doing it. But it requires you to solve this time-dependent Hamiltonian, which is very, very complicated. But I'll just give you an outline of what we do. So we use Fluke theory. In Fluke theory, what we do is we expand all of our variables in higher frequency powers. But writing it this way makes it look like you can never solve it because n can actually range from minus infinity to plus infinity. But what happens is your noise is actually not frequency dependent. So your noise will only act on certain n values. And you'll see that if you write down all the equations, after a particular point, n gets truncated. So you only need to go up to n equal to +3 and -3 in both sides. And you can actually expand it in the Fluke basis and find out the solutions of the time-dependent Hamiltonian. So once you do that, and you start looking at the noise again. So now if you start looking at the noise, that was the noise that we got where there was no back action evasion, but there was just some squeezing. You could break the quantum limit, but not the standard quantum limit, especially in low powers. But you can see that with back action evasion at higher powers, you can actually break the complete quantum limit. Okay, it does not work in the low power regime because the short noise does not allow it to perform well. But if you can combine the two, then you can see that you can even break the S12 at lower powers. So in some way, you can decrease both the short noise as well as the radiation pressure. Okay, so how does it affect the overall sensitivity of the system? So you can see that the optimal sensitivity of the system is always achieved. So this figure is actually enhancement in Debye units, like in noise units. So the optimal sensitivity is always achieved when you're doing squeezing alone, because that's where it kills off the short noise, especially at low powers, and gives you the best sensitivity. But you can see that BAE actually does very, very poor. So the red solid line is the BAE. It does very, very poorly in terms of sensitivity. At higher powers, of course, if you keep on increasing the power, your sensitivity would keep on increasing. And at higher powers, you basically go into a regime where none of this actually matters. But if you can combine squeezing with back action evasion, then you can see that you can get good sensitivity at good enough, at particular power, where you can actually even break the S-square. So there are regions in which even the sensitivity is high, as well as you've managed to break the standard quantum limit. So it allows you to do both of that in this kind of system. Okay, so with that, I will conclude. So am I early or is it fine?
I think it's just.
Oh, okay, perfect. So in conclusion, what I try to motivate today is, so theoretical study of collective states and hybrid architectures, they offer a rich playground to do a lot of interesting quantum things. And I believe like there are a lot of techniques you can use from many body physics, open quantum systems, and you can bring them together and make them talk to each other to even get new uncharted regimes which have not been explored so far. And we are looking at various aspects: information storage protection, communication sensing. We're working with Kero on error correction using collective states. And yeah, there are a lot of other interesting problems. So I think, yeah, studying theoretical notions connecting to them is actually a very, very interesting topic. So let me give a quick acknowledgement. So the first part, Elena and Matthias, they were involved in the experimental study that was done in IST and TU Wien in the group of Johannes Fink. And Rahul Gupta, he was one of my senior PhD students who worked on the second project. And we had some discussions with Mishkat and Pardeep, who introduced us to some of these toroidal BEC problems. Okay, so this is a quick picture of the group and the various people at IIT Bombay. Ruchi, who is here, he also is collaborating with us and with Carol. And yeah, and I think all the people on the right have actually left this year, so the group is much smaller now. And before I finally leave, I would just want to give you a brief overview of what kind of quantum activities are going on in IIT Bombay. So I think in the last 1 or 2 years, we came up with the Quantum Center, which focuses on information, computing science and technology, and under a lot of various aspects that we are trying to look at. Particularly, there are 3 main aims of the center. One is research, the other is outreach, about how like taking quantum knowledge to a wider range of people, including from smaller colleges and universities to industry, as well as teaching and training people. We have like 15 plus associated faculty members, quite a number of projects, and we are trying to build up like state-of-the-art fabrication and measurement infrastructure. And we've partnered with a lot of different government agencies, and also we are hoping that the National Quantum Mission in India, which is promising a lot of money to be available for quantum research, we will be a part of that. Okay, so with that, yeah, let me thank you.
Yeah, very interesting talk. So I think we have time for a couple of quick questions. So anyone want to ask questions? So while we're waiting, maybe we can start. So I'm wondering how good is the DMG method in comparing to the standard method people using, say, if we are extending the mean field to qubit expansion, so that how much better is when comparing to the first order qubit expansion?
Yeah, so I think for certain kind of states, it actually doesn't work. So for qubit expansions, so I think there was a study where people tried to look at a lot of different higher kind of cumulative expansions. And it shows that there are certain regimes in which first and second order is very good at capturing all of the quantum dynamics. But there are certain critical regions where even going up to really high number of qubits does not capture the entire dynamics.
Okay.
So one result that I had is, I think we didn't put it anywhere specifically, but if your states are closer to coherent states in some sense, then qubits are very good at capturing those kind of
spin coherent state.
No, even your input light states are close to coherent states, because then the correlations they develop are also similar to spin coherent state.
Yeah.
When they talk. But if you have like say a very strong superposition of 0 and 1 between the Fock states, then qubits struggle to capture those kind of non-classical states.
I see. Okay, but the method of DMG basically it works for arbitrary state.
Because here, apart from you throwing away some finite eigenvalues, it is exact. So
Hmm.
if these eigenvalues are all zero, then it is an exact method.
Mhm.
But you will end up throwing some of out some of it.
But is that kind of variation method efficiency? Because it seems that every time step you need to do some optimization.
Yes. So it's very time consuming. So it's
Okay.
not efficient in that sense.
Okay, I see.
But so you'll have to. So the idea is you have to take one spin out, apply the operator, and then renormalize the space again.
Mhm.
Again, take another spin out, again renormalize it. So you're doing it once in a like you're doing it sweepwise. And
Okay.
if the bond dimension is high, each of these steps will take really long to complete.
Okay. Any questions from the students from the other institutes? So if not, for the sake of time, let's thank the speaker again.